detailing for increased breakout capacity of steel anchor rods and concrete podiums. Kind of a mouthful, but we will be going over this information here today. So as Maria mentioned, I am Scott Fisher, and I'm a structural engineer here at Simpson Strong-Tie. And my background includes 9 years working in the design field. And now I've been with Simpson for about 16 years, coming up on 16 years. And I've worked both on our concrete anchorage side and now as our engineering lead of our Strong Rod Systems ATS product line. I do also want to recognize a few of my colleagues who were involved in the testing and the analysis for this project. And this was over a time span of several years. In particular, I do want to acknowledge Steve Pryor and Emery Montague. They both helped with our testing and our analysis, and they were major contributors in assembling our slides and discussion flow for today's presentation. And I'd also like to recognize Frank Ding, and he was heavily involved in our nonlinear numerical analysis that we used as a tool to basically to better understand some of the testing that we performed over the duration of this project. So now with that, I'm going to go through just a bit of a history that's taken place over the last several years. And kind of this history, this background kind of led to the findings and the output that we're going to be talking about today. So in order to understand how we got to where we are today, we do have to go back a number of years. So our testing and our study started out as a partnership with the Structural Engineers Association of California, as did an earlier project that we collaborated on that covered sill bolt anchorage. So as many of you know, the 2000 IBC introduced the current method of calculating concrete breakout, and that's known as the CCD, or the concrete capacity design. And that was incorporated into the 2007 California Building Code and also adopted into the 2006 IBC. And then from there, people started seeing, kind of the reality of the impact that these provisions had, specifically as they were related to sill bolts and to light frame construction. The design capacities for these conditions were so low based on the design equations that were in the code that the number of bolts that were required per the code for a standard shear wall began, I'm sure many of you will agree, they began to feel very excessive. And so we were approached by SEOC, where we began to work with them on testing sill bolts in concrete to reestablish the values. Now this led to the code changes into essentially the code that we have today. So now moving forward into 2011, 2012, we started to take a look at a kind of a different problem associated with structures built for densely populated urban areas. These structures typically have 3 to 5 stories of wood, light frame construction over relatively thin, elevated concrete podium slabs. And they utilize wood shear walls that see, in general, pretty high overturning loads imparted on these relatively thin concrete podium slabs. And we saw a lot of typical details that were associated with full building height rod systems. For example, here's our kind of an elevation here of our Simpson Strong-Tie ATS system. And then for these, the rods at their base had an anchorage basically embedded in the concrete, very similar to what we see here. Click ahead to the detail, where there was a termination at the cast in place anchor bolt. And it wasn't unusual to have the anchor cast in the concrete instead of below the slab. And by casting the anchor into the concrete, it's basically then protected against corrosion, protected against fire, vandalism, and any other external effects. And we typically like to see the detail being a cast in place sort of solution. So to get a reality check of some of the actual calculated demands, we're going to take a look at some of the typical loads associated with 3, 4, 5-story structures over concrete podiums. So in the second column, I'm going to grab my pointer here. Second column here. So we have what we're describing here as the likely rod system. And here we have 3/4 inch mild steel with the strength of 58 KSI all the way up to a 1 1/4 inch high strength rod. There we go. And these resulted in demands that we're labeling 1.2 times the nominal tensile capacity. And there's a reason for this description that we're going to talk a good amount today. Now, the 1.2 times the nominal tensile strength will result in the values that we see in the third column. And these are ranging from 23 kips, as you can see there, all the way up to 138 kips. Whereas if you calculate the nominal capacities for these installs, where you have over here the edge and away from edge, you'll see that while we may need to resist around 138 kips demand, we're only calculating a capacity of about 51 kips. So there's a bit of a disconnect between the demand and the capacity. And we'll come back to this table shortly, and we'll kind of walk through some of the numbers that we have here.